We were studying jitter generation, and one of the types of jitter that you see when you use the bang bang phase detector is bang bang jitter. Okay, it's a systematic jitter that happens. Even if you have jitter free input data, the clock will be jittering back and forth. And this, the amount of jitter is related to the bandwidth. Basically, you try to make the bandwidth of the loop higher, the more the jitter will be. It is also proportional to the latency. The more delay you have in closing the loop, the more bang bang jitter you will have. Okay. So these things we saw. So we saw that so this is alternating data. Okay. And the clock is here. Okay. The way we make the bang bang detector, these samples from which we determine whether the clock is early or late, they change over there, right? Okay. And essentially, the information about this transition appears there. It's because of the delay that we have something like this. And we saw that at a minimum, you will have two consecutive ups and downs, right? Because of this delay. And the phase will do that. It will ramp up and then ramp down for 2 cycles and ramp up for 2 more cycles and so on. Okay, and we were able to calculate the peak to peak value here, right? And like I said, if you try to increase the bandwidth, which is basically increasing the product ICP times R times KVCO, this will also increase. So that also limits the bandwidth. You may want a very high bandwidth for tracking jitter in the input data, but if you do that, the systematic jitter generation increases. Okay. So now before we go further, this is of course alternating data, right? So what do you think happens if you have, data that is more representative of random data, right? You don't always necessarily have all the transitions. What will the phase look like? Or what will the bang bang jitter be? Will it be the same as this or more than this? Say less than this? More. Why? What will happen to the phase when there is no transition? Remember again, the system we were considering was one where VCO was at the exact frequency, and you are only providing phase correction through the loop. Okay. This is analogous to assuming a very large capacitor, so that in each cycle the change in the capacitor voltage is not much. So then what do you think happens? How much will be the bang bang jitter? So what will the same phase curve look like? Maybe I'll draw it bigger. Essentially, you have to kind of imagine what happens when there is no transition. Okay. So if this is edge number 1, 2, 3, 4, 5. Okay. So this edge 1 is the clock transition corresponding to that is too late. So that's why you are getting an up signal which is ramping up the phase. Okay. In response to 1, you are getting an up. In response to 2, you are getting an up, then 3 is down up to here, and then 4 is down, and so on. This is what is happening. So what do you think will happen with random data? Okay, then, yeah, that is true. But what will happen to the bang bang jitter? Reduces? The peak to peak remains the same. What happens is that, so here I have transition 1, but I don't have the second one, right? So in response to transition 1, you will still get an up signal. Let's assume that. Okay, and at 2 there is no transition. Okay, so there is no correction. The VCO is still operating at the right frequency. We'll assume that, right? That is, we assume that the amount of charge injected within a single period is not enough to change its frequency, right? The capacitor is very large. The loop filter capacitor is large. So the phase remains like this. Okay, phase remains the same. So what happens at, if I call it edge number 3, what happens now? What will you get? Will you get an up signal or a down signal? Down. Why? See, earlier what was happening was, at 1 you got an up signal, the phase of the clock advanced. At 2 you got another up signal, the phase of the clock advanced. You got an up signal at 2 because the clock was still too late. Okay. So now here the clock position has not changed, right? The clock is still too late. So you will get another up signal now. Okay. So the whole thing is, I mean, essentially the process freezes when you don't have transitions. Okay. So earlier you were getting an up signal followed by another, immediately followed by an up signal. Now there will be a dead time, and after that you will get an up signal. I am assuming that the change due to a change in the capacitor voltage is not appreciable here. Okay. So then I have another transition here. This 4, this will give me a down signal, because by now the phase has become sufficiently advanced. Okay, and I have an immediate edge at 5, I will get another down signal. Okay, and then there is no edge here, so it will stay there, and so on. Okay, so you can imagine this triangular wave, but now it won't be continuous. There will be parts where it is just held constant. Okay, but the peak to peak will remain the same. Is this convincing? So this is not, the calculation that we made is not dependent on the transition density. Of course, if you get a really long period with no transitions at all, then the capacitor voltage will change and the frequency will change and things will change. But if you don't have that, so this is okay. This kind of calculation is fine. Okay. Is this okay? Any questions? See, the clock phase, first consider the case where you have transitions every time, right? So this edge is, the first edge is late, that's why you are getting an up signal. The next edge is late, that's why you are getting an up signal. Okay? Because you get two up signals, this edge has become early, okay, and this edge is also earlier than the data transition. Okay, so now essentially starting from this point you need 2 up signals to make it early. Okay, now you have got 1 up signal here in the case where I am having random data, right? You got 1 up signal, so this clock edge will still be late and it's not corrected by the time it comes here, right? There is no further correction now. So I have to write it in an exaggerated way. So let's see. What happens is, how does let's assume that these are the data transition instants. Now how does the clock and data recovery work? So let's say the first edge is too late. Okay. So what does the CDR actually do? It will apply an up signal. So that means that it will increase the frequency of the VCO. So the next cycle will not be as long as this. This is the nominal cycle length. but the next one will be a little bit shorter. Okay, so that's the only way it will bring the edges to the left, isn't it? And then if you have another transition here, it again sees that the edge is late and it will make it even shorter. Okay, so now it has become early, right? So this is late, and this is early. Now if there is no transition here, this cannot happen, right? It will be at the nominal it will be at the nominal period, so that means that it will go over there. So here we get a late measurement, here we don't have any measurement, and here you get another late measurement. So that's why it will freeze like that. Is this okay? So you can only measure when you have an edge. You can only measure and correct when you have an edge. If you don't have an edge, the phase will remain the same. So that's why, I mean, you imagine this, the way the clock and data recovery works, the clock and data recovery with the VCO is, when you have plus ICPR, it is speeding up the VCO. If you have minus ICPR, it is slowing down the VCO. It speeds up the VCO to move edges to the left. It slows down the VCO to move the edges to the right. Okay? Is this fine? So that is about bang jitter with random data. So the calculation is the same, but you just have to imagine all these things to convince yourselves that the peak to peak jitter remains the same. Okay? Now, next we will go to a slight modification of the bang phase detector. Essentially what happens is that as you go to higher speeds, right, you have to generate this high speed clock. That clock is what is driving all the data, the decision latches and all the other latches or flip flops you use in the phase detector, right. So now as you go to higher and higher frequencies, this clock distribution, that is the buffers that are used to drive the clock, consume a substantial amount of power. Okay. And then also as you go to higher and higher frequencies, it becomes harder and harder to make a clock that approximately looks like a square wave. Okay. And beyond some frequency, you get some sine wave and some rounded waveforms, the amplitude reduces and you can't drive it at all. Okay. Or if you have to drive it, you have to burn a lot of power. Okay. So that's why there is some interest to try and not have the clock at the highest frequency, right? Reduce the highest frequency of the clock that you have to distribute. Okay. So that is the motivation behind you sometimes have half rate or even quarter rate architectures. Okay. So let's look at the half rate bang phase detector. What is meant here is the following, like the data rate is still the same. So let's say the data rate is 10 gigabits per second. So then in a full rate phase detector, the clock will be at 10 gigahertz, right? It will complete one cycle in 100 picoseconds. In a half rate architecture, the clock will be at 5 gigahertz. That is, you don't see any single waveform that has 10 gigahertz frequency. Now, of course, the data rate is still the same. We are not talking about a case where reducing the data rate, right? That's not the idea. So if you reduce the data rate, then you can't send as much data. That's not what we want. We are now looking at some circuit aspect of this where we are still processing 10 gigabits per second of data, but the maximum periodic clock that we have in the system is at, the maximum rate of the periodic clock is at 5 gigahertz. Okay. Is this fine? So we will see the motivation for this. This is not exactly the same as having 5 gigabits per second data with 5 gigabits per second 5 gigahertz clock, right? That's not what we are talking about. So now how did we do this is data. Again, I am drawing alternating data, but you know what happens in reality. Okay. Now when I had the full rate clock, by the way, how do we do the bang phase detection? We look at 3 consecutive samples, here, there and there, and by using some combination we find out whether the clock is early or late. Okay. So let me draw the clock maybe slightly skewed from the data. For each phase detection, for detecting phase at each edge, you will need 3 samples, right? And that we were getting by when you had a full rate clock. By sampling at the rising edge and the falling edge. Okay. Alternatively, I can think of it as a two-phase clock. I have a clock and I sample at the rising edges of this, and I have the inverted clock or 180-degree phase shifted clock, which will look like that, and I sample at the rising edges of that. I am showing this to show sampling only at the rising edges of the clock. In practice, all these clocks are like fully differential, so you will have both these waveforms anyway, and when you want a rising edge trigger, you connect the clock in this way, and when you want falling edge triggered, you just swap the differential clock length. So this is a reasonable view of what happens in reality also, the practical reality. Okay. Now, what we don't want is a waveform that is like this, right? A waveform that completes full cycle within one data interval. Okay. But we still want all this information about phase detection. So, how many phases of the clock do I need? When I had the full rate, I have 2 phases of the full rate clock, right? If I have only a half rate clock, how many phases will I need? Huh? I mean, I assume that again, even with the half rate clock, I will be sampling only at the rising edges of the clock. So how many would I need? Yes, Joseph, what is it? 4, yeah. So let's say, I mean, let me draw one half rate waveform. It will look like this, right? I will sample here and there. That is, I will get this sample and then that sample. Okay. Now, this is CK0. Now I need this one. To get that, I need, what phase shift do I need at this frequency? 90 degrees, right? So, I will be sampling here. That gives me that one. Okay. This is CK90. And if I take the 180 degrees phase shifted clock, I will get that sample. Is that enough? Because for the next phase detection or for the next edge, I will need this one and a sample here and a sample there. Okay. So I will need an edge. Actually, this, I think I drew it in a probably a little too long, but this is what gives me a sample over there, right? That clock 0 gives me a sample here and a sample 2 cycles after that. So to get this sample, I also need the 270 degrees clock, which is just opposite of that one. Okay. This rising edge will give me this clock. It's not to scale, but you get the idea. Okay. It's also not hard to imagine. So instead of 2 phases at the full rate clock, I will need 4 phases at the half rate clock. Okay. Is this fine? So all the information that we have can be obtained from 4 phases of the half rate clock. And this is kind of what you expect also. If you want to implement the same circuit, same functionality, that is if you want to process a certain amount of data in a certain way at a certain rate, then you can either do it at some rate or you can do it with twice the circuitry at half the rate and so on. This is the standard parallelization, right? So that is roughly that is the same as what's happening here. Okay. So I'll have 0, 90 and 180, and combining all these I will get one phase detection which corresponds to the timing of this edge, whether the clock is earlier or later than that edge. Okay. And then I can combine this 180, 270 and 0 to get the timing of that data transition with respect to the clock edge. Okay. So when you implement all these things, there will be a lot of details in the implementation to combine the information, but I am just giving you the conceptual stuff. Okay. So and then again it repeats. So for the next one, you again combine 0, 90 and 180. Okay. Yes. Correct. Yeah. But the waveforms will be, the period will be twice as long. We'll see what advantage it has, right? No, I mean you still, of course you have to, because without, if you don't want to lose information, somewhere you have to have the delay, which is basically half the data symbol period. But the implementation, it still has some advantages because especially in a technology, as you go to higher and higher frequencies, from very low frequencies if you start off, right, if you make, if you let's say double the rate and half the amount of circuitry, you will consume the same power. But as you go to higher rates, it turns out that the implementation becomes more and more difficult and the power increases more than linearly with frequency. So at that point, it makes sense to go to half the rate and then do this. Okay. Yeah, you still have to produce the enough edges to cover all the samples. Okay. So the spacing between these two is still Ts by 2, right? I mean, obviously you are using like a 90-degree phase shift at half the rate or 180-degree phase shift at the full rate, which corresponds to the same absolute time interval. Okay. So you sample the data, input data with 4 flip-flops now, and I'll show all of them with rising edges but show different clock phases. Okay. Then what? Just think of the earlier bang implementation. What else should we do? Huh? Yeah, how do I do that? I mean, I need to first realign them properly, right? So here, first of all, I am combining, I mean, here 90 means 90 degrees lag. So I have to combine 0, 90 and 180, right? Okay. Huh? You have to? Yeah. So you have to sample again at This is one way. There may be alternatives, but we'll follow the same thing that we had used. Okay. So let's see if we need this. Actually, this is not what we wanted. So if we do this, okay, so this will be the A sample, this will be T, and this will be B, right? This is the first set, this is this set, okay, and now these will all be aligned in time, okay. Then you can do the XORing. Like this, you can get up and down for this set, okay. What do you do for the next one? What do you do for this? Shivam, what is it? Yeah, you have to retime everything to clock 0 now. It will be like this, and then so now for this again, these will be time aligned samples. This will be A, this will be T, and this will be B, right? I will bring it down. And you can do the XOR to combine these things to get up to and down to, okay. So I am trying to keep everything exactly the same as before and do this. There are many other options as well, right, which you may want to investigate in a practical scenario. For instance, you could implement only up one and down one. Then you will be losing information on half the transitions. The alternate transitions you don't get, and that's all there is to it. I mean, if that is acceptable to you, you can do that. In implementation, there is a lot of freedom. Sometimes you can do that. So if you kind of deliberately omit half the edges, what happens is your essentially your transition density has effectively become half of what it was, right? So then your bandwidth can be lower and so on. But if you do these things, if you do this up 1 and down 1 and up 2 and down 2, you can get exactly what you had before. Exactly in the sense, all the information that you had before. But still, earlier the up and down, each of those pulses was one cycle wide, right? One data symbol period wide, and these will be, how wide will they be? There will be 2 symbols wide. So you can combine them, for instance, in a charge pump. Okay, and what should be this current? ICP by 2, so that essentially for each up you will get the same amount of phase change in the VCO. If you want to keep everything the same, this is what you have to do. And then similarly, these should be, this is one possible implementation, right, to do this at half rate, and then you can just connect these things in parallel, okay. This is fine. Just imagine that you are getting, I mean your clock is lagging the data, then you are getting up signals in both up 1 and down 1, and then you will get a constant current of ICP, okay, which is what you were getting earlier also. Is this okay? So this will be exactly the same, but there are many other options. That is, you may not want to process both of them, or you may want to take, let's say, the major, I mean, you take sort of OR of these things or something, right? There will be some sort of nonlinear combination. That is what I am saying is, if let's say this one, if the up one is high and down one is 0, and up 2 is 0 and down 2 is high, you may not do anything at all. Okay. So I guess that is, I mean, you can do that with a logical combination instead of adding up currents. That is what is happening here, right? In the common period, if up 1 is high, this current will be going there, and if down 2 is high, that current will be going that way. Okay. So you can do that probably with a logical combination also. Okay. So those things are there. Now what advantage does it have? The data is still running at this speed, but the clock is at half the rate. Okay. So again, it's not the same as running everything at half the rate. Then the latches will become better, the dynamic gain of the latch will be better, and so on. But still, for instance, the aperture and the setup time and so on for the flip-flop should be the same, because the data can change in that time, right? But because the clock is elongated by a factor of 2, you do have more time for regeneration. So your latch implementation and these things become better. Because the waveform has a longer period, it can settle better, etc. So some things do become better with this. I mean, this kind of thing usually makes sense if you cannot comfortably make the full rate, or you have to burn a lot of power. Like I said, you take any circuit, whether it is analog or digital, you can go on increasing its frequency by burning more and more power. And at low frequencies meaning at frequencies which are comfortably possible in a given process, the power dissipation or the current consumption usually increases linearly with frequency. And at some point it starts becoming super linear. Okay. And at some point you can't make it at all, because you try to increase the size of the devices to increase the GM, but then the self-capacitance loading increases in the same proportion and the speed doesn't increase at all. Okay, this is what you would see, and you would have seen in some simple experiment, I mean some simple examples we have considered in assignments and so on, right? So it doesn't work at all. So at that point, essentially, if you plot the power consumption versus speed, it goes linearly and then it starts going up like that. But if you are somewhere over here, it makes sense to come to half the rate, because then the power savings will be more than half, although you have twice as many flip-flops. Okay? This is fine. So this is the motivation for half rate, and sometimes you even go to quarter rate. Okay? This is still a sort of analog implementation, right? We still have these charge pumps, but we are kind of using every waveform here. These waveforms will have twice as much period as the single period, so it will have better settling behavior and things like that. Okay. Setup hold time constraints are the same, because the input data is at the same rate. And typically half rate architectures take approximately twice the number of components. It may not be exactly twice. If you look at our full rate detector, it has some number of latches. This may be about twice the number of latches. Okay. Any questions about this, the half rate phase detector? What is the latency we have now? Is it? When does the information about this appear? It's still the same. The way we have implemented it, it is still the same because the information about this edge appears at this 180 degrees clock, right? So it is still half a clock cycle. Okay. Same latency as before, the way we have implemented this. Okay. Now, if you want to do the logical combination, for instance, if you want to see if up 1 and down 2 are high, you don't want to do anything and use a single charge pump circuit, right? Then you have to delay one of them by half a cycle, right? There is no other way because now actually this up 1 and down 1 are changing at some instant and this up 2 and down 2 are changing at the next half cycle of the clock, right? If you want all of them to change at the same time so that you can use a single charge pump, you have to delay one of them by half a clock cycle. So that means that on average, for some of the transitions, you have a delayed measurement. On average, the latency has increased. Okay. Is this fine? Okay. Now, so far our implementations have been analog, whether with or without forwarded clock, right? With forwarded clock, we have basically essentially a delay line whose delay changes in response to some control voltage, and then our loop updates that control voltage. And without forwarded clock, we have a VCO which generates the new frequency, and you basically adjust the frequency and phase of the VCO through this loop filter. Okay. Now, increasingly, there is more and more interest to go towards digital architectures. By digital architectures, it's easiest to understand with the case with the forwarded clock. Actually, exactly the same thing also works for the case without the forwarded clock. So, what is digital now? We have data, we have clock in, and instead of this analog delay line, okay, you imagine that you have a digitally controlled delay line. That may not be how you implement it. It's not a delay. It may be that you generate a number of phases of the clock and you pick one of them. That is typically how it is implemented. But essentially you have delayed versions of the clock, and as far as the external model is concerned, it's like having some control n. So the delay of this is proportional to, let's say, n control. Okay. Or to keep it similar to what we had before, you can make it some n max minus n control or something so that it has a negative slope. Let me do it like this. So what it means is, I mean, how we implement it is, we'll come to it later, but most often one of the possible implementations is you can make a delay line and then switch the delay lines in and out, or you have a circuit which generates like a whole bunch of phases, right? And then you select one of them. It's all the same thing. So you can have, they'll make a difference for implementation, but they work in the same way. Essentially, based on a digital input, you pick one of these phases. Okay. And this digital implementation, of course, the output of a linear phase detector is analog, right? It's in the information is in the area of the up minus down. So it doesn't make much sense when you want to generate this digital control. You can do that, but you will need an analog to digital converter to convert that information. So we'll assume basically a bang bang or a digital phase detector here. Okay. And from this you will get up and down signals. Okay. Now you interpret these as some digital signals, right? Either up is 1 or down is 1. Okay. And then you have some digital block which gives you this N control, right? Is this fine? So essentially it's the same thing. If you detect that it is too early, you adjust this N so that it becomes, the clock edges move to the left, move to the right. Or if you detect that the clock is too late, then you adjust N control so that the clock edge moves to the left. Okay? Is this fine? So let's first try to make it behave in exactly the same way as our analog loop. What did we have here? What was the loop filter when we had the forwarded clock? Just a capacitor, right? We have this ICP and a capacitor. We control. We also assume that this delay is, as V control increases, the delay decreases. This was our model, right? This is also ICP. I have not drawn it well, but you get the idea. So now let's do the same thing with digital implementation. Here we get these digital signals, and I have something here that let me show this as a phase delay. Okay, it shifts the phase of the clock by some amount, and this is the controlling number, and let's say phi d is some phi d 0 minus n control times phi LSB. Phi LSB is basically for unit change in n control, how much does the phase get shifted. Okay. And like I said, I want this and that to behave the same. What I mean is that if at a particular edge I detect that the clock is too early, something will happen here and this loop will provide some correction to the phase. And in the bottom case, I want exactly the same thing to happen. Okay. So how do I make sure of this? What should I calculate now? I want to find out what this phi LSB is, and I also want to find out what is inside that box labeled question mark. So what should that be? Okay, So first, how do you compute phi LSB? What should you do? This is V control C. What is that? Which time period? Yeah, essentially you want to make sure that the response to, let's say, a single up signal, in response to a single up signal, this phase gets shifted by a certain amount. How much is that? Huh? How much is that? Tell me. You get a single up signal here, okay? How much does the phase of this clock change? ICP? So if I have a single up signal here, this voltage ramps up by how much? ICP T naught by C, right? Is this correct? Okay. And that causes a phase shift of how much? ICP T naught by C times? Huh? Yeah. So it is omega naught KD or 2 by F naught KD. Okay. So what is this number now? What is it? What is T naught times omega naught? 2 pi. So basically this whole thing becomes 2 pi ICP KD by C. Okay. Does this make sense? Is this okay? Yeah. So this has basically dimensions of phase, or basically has no dimensions, and this is the phi LSB that you want to make it the same as that. Now that may or may not be implementable. This number may come out to be too small. Okay. I don't know. You have submitted the assignment already, right? What is KD? What is ICP? What is C? Just tell me what is. ICP is 100? 104. Okay. Let's say 100 microamperes. KD? 120 picoseconds per volt, and C 1 picofarad. Okay. So how much is this now? Let's make it 100 picoseconds for simplicity. This pico goes away, and then you have 10 to the minus 2. So this multiplied by 2 pi is the phase. So this is the unit interval, right? 10 to the minus 2 ui. So that means that how many phases do you need in a cycle? 100. So you have to basically, your phase selection block should provide 100 phases so that you can pick this exactly. So it may be doable. It is kind of on the border of being doable, because the more phases you have to generate, you also have to distribute those things, and that can become a problem. But you get the idea, right? If you had, if you divided your clock into 100 phases, right? If you got a 100 phase clock, you can pick one of them and do exactly what we were doing earlier. Okay. So what is the next thing? So what should be inside this? Should basically be a counter, accumulator, right? Essentially this is an integrator, right? So that should be an accumulator. Okay. Accumulator what? What should be the input to the accumulator? Up minus down. Okay. So you need a digital subtractor. Of course, this is just one bit. So you can have an up down counter, and up controls, up makes it count up and down makes it count down. Okay. That I will show as up minus down, and here I have an accumulator. Okay. And this will do exactly the same thing. Is this okay? If I assume that phi LSB is 2 pi ICP times KD by C, it will do exactly that. It's not that it should do, I mean, we should start from an analog design and go to digital. We've already done that, so I did this. Okay. and the values kind of gave you an idea of how much the 5 LSB should be. It should be such that it should be basically 1 cycle by 100 in this implementation, but that is typically the case. Okay, that corresponds to about a 7-bit type resolution, right? Typically, when you make digital implementations, you make everything in powers of 2. Why is that? What should happen to this accumulator? Actually, this accumulator, let's say you go on getting up signals, it will keep on accumulating. What should actually happen? Huh? Supply voltage. There is no, this is a digital stuff. So what should happen to the output? Yeah. Okay, for this particular case, we have 5 LSB to be corresponding to 100 to a UI, right? So what should happen to this counter? Yeah, it will wrap around. At what number should this wrap around for this particular implementation? Huh? No, why 127? No, I'm saying like what did we compute 5 LSB to be? 2 pi by 100, right? So when should it wrap around? Yeah, it should go up from 0 to 99 and then wrap around, right? Basically, if you go all the way to the most delayed one and then you wrap around and so on. Okay. So this should wrap around for after 1 cycle. Okay. Because I mean, you can try to implement like let's say 200 phases so that it spans like 2 periods, but that's a waste. Typically, this is a phase selection block and all the phases together will span 1 cycle. So if you go past 1 cycle, you have to wrap around and come back. So now the way we have done it, if we make this LSB, the phase increment to be 100th of a cycle, this has to wrap around after 100 steps. Okay. So that's why, I mean, it's a lot easier in binary computation to make it wrap around after, let's say, 2 to the n steps. So that's why you don't divide it into 100, you divide it into either 64 or 128 and so on. Okay. But you get the idea, right? This business of digital clock recovery, that is essentially phase selection based on this digital phase detection. Okay. Now this is for a case with a forwarded clock. We'll see for a case without the forwarded clock. How does it work? Without the forwarded clock, you have to correct the phase as well as frequency. Will it work? Anyway, think about it. We'll discuss it in the next class. Okay. And we'll also discuss the advantages of this. We don't go to digital just for the sake of doing it, right? It provides some advantages. That's why we do that. Yeah, you don't normally produce 100 phases. You may produce like 4 or 8 from a quadrature oscillator and so on. Okay. And then you can do this phase interpolation. You can do weighted addition of successive phases. So for instance, if you have an edge like this and if you have another edge like this, it should be like a ramp. It can't be like a step. Okay. So then if you take, let's say, another voltage which is alpha times 1 plus 1 minus alpha times 2, what will that look like? This is the zero crossing. That will have a zero crossing where this time is alpha and this is 1 minus alpha. By doing this, you can, by doing this weighted addition, you can do phase interpolation. That's how it is done. Okay. Now you can't do this. If 1 and 2 are very far away. They have to be kind of close so that the ramping periods have some overlap. Otherwise, I mean, imagine if you do this with steps. Okay. If you do that, what will happen if you take alpha times 1 plus 1 minus alpha times 2? You will get some waveform like this. That's not what you want, right? But okay, you can find. I mean, anyway, at higher frequencies it will be slower, and if it's not, you have to deliberately slow it down. Okay. This is fine. We can discuss the implementations later, but that's how it is done. You certainly don't distribute. I mean, you don't generate all 100 phases and distribute them everywhere, because now the power involved in distributing that is also enormous.